Hi, so in this video, I want to go over some of the ways in which we might derive an equilibrium constant from a similar reaction or a similar equilibria. So this is kind of similar to stuff that you learned when starting off Hess's law, right? When it comes to taking a given chemical equation and kind of manipulating it, right? Kind of flipping it around or multiplying it by a factor, how that changed the enthalpy change of reaction. Here we're going to see kind of a similar property, but instead regarding the equilibrium constant, or K. So to begin here, I want to start with this reaction where I have just generic reactants A and B turning into product C. Now, if I have a balanced chemical equation like this one, where everything is in the gas phase and I have 1 mole of A plus 2 moles of B producing 3 moles of C, then from this we can just write out the equilibrium constant expression for this reaction. So maybe not an actual number, but instead just in terms of different concentrations, right? How would we write that equilibrium constant? So you can go ahead and just pause the video, take a moment to think about how you might set up that equilibrium constant expression, and then I'll start up again in just a minute. All right, so hopefully you've taken some time to write out what the equilibrium constant expression would be in terms of concentrations. Now for this reaction right here, or for any equilibrium, right, we always set it up as the products over the reactants, and then each of those chemicals is to whatever power their molar coefficient is. So in this case, right, for this particular equilibrium, we would write this as K, the constant, equal to the concentration of C cubed, because the molar coefficient of C was 3, and then that's divided by the concentration of A and the concentration of B squared. So here, right, in this expression, these are specifically referring to the equilibrium concentrations. That's what the little EQ down there is referencing. But right, for generally how we set up these expressions, we always just have the products over reactants, and then to whatever power the molar coefficient is. Now what I want us to consider here is instead a kind of similar reaction, but instead reversed. So here I have reaction 2. It looks exactly the same, but the products and the reactants are flipped. So now it reads as 3C producing A and 2B. Now again, for this, I want us to consider what the equilibrium constant expression would look like for this new reaction. So again, pause, write this out, and then we can kind of compare answers. All right, so again, with that same process of writing out the equilibrium constant in terms of concentrations, here with this new reversed equation, we're going to see the concentration of A times the concentration of B squared divided by the concentration of C cubed. Now what I want us to consider here is how these two reactions compare and how these two equilibrium constants compare, right? If you look at the first reaction versus the second, we see, right, that we're basically just flipping or reversing the reaction, right? Switching what the products and reactants are, but not changing anything else there. Now looking at the K constant, right, and the expression that's used for that, we can kind of see how they are similar to one another, but the key difference is that, right, because we've switched the products and the reactants, we've essentially switched the numerator and the denominator. What we've done here, kind of to make our second K constant from that first one, is just taken the inverse of that original K constant. So right, by reversing a reaction, we're essentially saying that the new equilibrium constant that comes from that reversed reaction, that's equal to 1 over our original K constant, right, or the inverse. So reversing what the products and reactants are just gives us then a flipped K expression. What that means numerically then is that the number that we're going to see is just going to be inverted, right? So 1 over whatever our K1 value was, that gives us K2. All right, so that's one common way that we'll see different reactions be manipulated. Another way that we can consider is actually changing the molar coefficients as well. So again, looking at the same reaction 1 that we had before and that same K expression for reaction 1, now I want us to consider a third reaction. In this case, we've changed the molar coefficients. We've basically doubled everything. Now this new reaction that I have written below, it's still balanced. It's still technically the same reaction in terms of our ratios of A, B, and C, but now just the molar coefficients, each one has been doubled here. So I have 2A plus 4B producing 6C. Now again, I want you to write out the K expression for this new reaction. So again, go ahead and pause, and then you can take a look at the answer in just a moment. So right here, the K constant I found for reaction 3, which we'll call K3, is written out as the concentration of C to the 6th power divided by the concentration of A squared and the concentration of B to the 4th power. So again, the same process goes. It's the same idea of just taking our products over reactants and then putting those to whatever their molar coefficient is to that power. Now, again, kind of looking at how these two K constants compare here, if I look at K1 versus K3, where all of the different concentrations are, that stays the same. So like C is in the numerator in both of them, A and B are in the denominator. So that piece isn't changing here. But what is changing is the molar coefficient and the power that each of these concentrations is going to. What I've essentially done in doubling this reaction is I've taken each power that these concentrations are, and I've doubled them, right? So what that looks like mathematically is essentially squaring our entire K constant, right? How K1 compares to K3 is K3 is essentially K1 squared. And so this can be expressed through this kind of relationship right here. If we take a reaction and we take all of the coefficients and multiply them by a factor, then the K constant gets put to the power of that factor. So right here, because I've multiplied all of my coefficients by 2, the K constant is then going to be squared, or we're going to take K1 and put it to a power of 2, thus giving us K3. Now this works even if we have, say, like a fraction as our factor that we're multiplying as well. So for example, if I were to divide the entire reaction by a number, that would be kind of like just multiplying by a fraction. In that same way then, the K constant would just be taken to the power of that fraction. So we can take a look at an example right here just to kind of put these different ideas together. So say here we're given the following equilibrium. We've got 1 mole of N2 plus 3 moles of H2 producing 2 moles of NH3, all in the gas phase. And here we have a K constant of 5.6 times 10 to the 5th power. Now, my question here is, right, using that information, what would be the K constant for a similar reaction written below? So below, there's a second equation. We've got 1 mole of NH3 producing a half a mole of N2 and then 3/2 moles of H2. What would be then the K constant for that reaction? And here I want an actual numerical value. So go ahead and calculate this out, right? Think about how we've changed the two reactions and how that would then change the K constant as well. Again, you can pause, and when you're ready, we'll move on and show the answer and everything. All right, so having given this a minute, right, hopefully you can see kind of what changes were made to the reaction itself. If I compare my given equilibrium to the one that I'm trying to solve for down below, I can see kind of like two major changes there. For one, I've reversed the equation, right? I've switched where the products and the reactants are. And for two, I have basically divided the entire reaction by 2. All of those molar coefficients are essentially multiplied by a factor of 1/2, and so that's shown in my new equilibrium. So what that means then is that my K constant that I'm going to find here is going to have 2 changes done to it, essentially, right? 2 changes to the reaction means then 2 changes to the K constant. Now the actual answer that I got here was 1.3 times 10 to the minus 3. Let's walk through why that is. So first, focusing on the changes made to the reaction itself. Again, as I mentioned, we've taken all of the molar coefficients and divided them by 2. That's essentially putting the K constant to the 1/2 power, right? So all my molar coefficients were multiplied by 1/2, and so the K constant that I'm given there of 5.6 times 10 to the 5th, I'm going to need to put that to the power of 1/2 to kind of match with that. Additionally, because this reaction was reversed, right, that means that I'm going to need to invert this K constant, or basically say 1 divided by that. Now I can combine both of these factors together, essentially saying 1 over the K constant to the 1/2 power, right? All of that together should handle both of the changes that are being made to this equilibria, thus giving us our new equilibrium constant. So actually plugging in the number here for K, right, of 5.6 times 10 to the 5th, I can go ahead and solve for this in my calculator, and I get 0.0013, or 1.3 times 10 to the minus 3. All right, so again, we see here kind of two examples of manipulating equilibria and manipulating the K constant that goes with that, right? Although these are very similar reactions, the fact that we're changing things like the molar coefficients and the product versus reactant, that's going to have an effect then on the equilibrium constant K that goes with that reaction, as we can see right here. Now, one last example of kind of ways in which we'll commonly see equilibria, again, manipulated, is again kind of familiar with some of the stuff that we saw when learning about Hess's law, right? So say here I have two reactions that I'm actually going to combine together. So imagine here reaction 1, which is again the same reaction 1 that we saw before with the same K expression. Now I have here a fourth reaction, which reads as 2 moles of C producing 2 moles of B. Now the equilibrium constant expression for this fourth reaction I have written off to the side as B squared over C squared, right? Again, just mimicking that products over reactants to whatever power the molar coefficient is. Now, again, what I'm trying to do here is add these reactions together. So essentially combining all of the reactants from both reactions and all of the products from both reactions, and then just like canceling out anything that may be redundant or the same on either side of the equation. So when I add together these two reactions, what I am left with is essentially just this new reaction, which we'll call reaction 5, and this reads as 1 mole of A producing 1 mole of C. So right, you can kind of see how certain redundancies are like canceled out when adding these two reactions together. For instance, in reaction 1, 2 moles of B are in the reactants, but in reaction 4, 2 moles of B are in the products. So because we have 2B on either side of this equation, when we add those together, they're going to just cancel each other out. And so that's why we don't see any B in the final reaction in reaction 5. Or in terms of the C, right, there's 2 moles of C in the reactants for reaction 4 versus 3 moles of C in the products for reaction 1. And so 2 moles are going to cancel out on either side, leaving us then with just 1 mole of C in the products overall. That's why we have then our complete equation of A turning into C. But so, right, this is just showing how the reactions add together. How do we think that's going to affect, say, the K constant for that fifth reaction, right? We think of the K expression for reaction 5, it would read as just the concentration of C divided by the concentration of A, as I've written out symbolically right here. But mathematically, how does K5 relate to K1 and K4, right? What kind of calculation would I do with those given K constants for our given reactions to make then our new K constant for this new reaction? So go ahead and kind of ponder this for a minute, right? Look at the expressions for K1 and K4 and see how you could maybe use them to match with K5, right? What kinds of calculations would need to be done there? Okay, so looking at my equilibrium constant expressions here, right, and again, trying to see maybe what kind of similarities or what kind of differences there are between K1 and K4 and K5, right, how I can kind of imagine I just putting together my K1 and K4 expressions to make K5 is if I look at all of the products, so all of the numerators, versus all of the denominators, all of the reactants, right? And see again maybe how things can cancel out. So for instance, if we look at like the K1 expression, we see concentration of B squared in the denominator. In K4, we see concentration of B squared in the numerator. So if I want to cancel those out, right, essentially getting rid of the B squared, as I don't see any concentration of B in my K5 expression, then what I can do is I can just multiply together K1 and K4, right? By multiplying those, the b squared that's on top of one expression is going to be canceled with the b squared that's in the denominator of another expression. When I multiply those two things together, I can then get my overall K constant for this overall reaction. And so that's to say then that when I add reactions together, as I have done right here, the equilibrium constant that results from that is simply the product of whatever those summed reactions were. So right, taking like reaction 1 and adding it to reaction 4, what I do over here is I take K1 and I multiply that by K4, right? That will give me then my new reaction's K constant. This is helpful for if we have, say, like a multi-step process that involves like multiple reactions kind of going in sequence with one another. Again, we kind of propose like similar ideas when talking about Hess's law, right? So again, if you have like a series of reactions that you're kind of doing in sequence, then the K constant for that overall process is going to be the product of all of those K constants for the reactions that were being done in sequence. But so, right, those are the main ways in which we see changes to equilibria and thus changes to K constants. Please let me know if you have any questions, and I'm always happy to help. Bye.